Hi guys, here is the video lesson on 11.4 compound events. This one has three total topics, inclusive and mutually exclusive events. That one isn't so bad or so different than what we have been doing. Then we've got our Venn diagram problems and our at least problems, those last two items. And those are going to be the ones that students typically have a little more trouble with. And so we've got a couple examples of each of how to use a really specific strategy to solve a couple of really specific problems. So here we go. Mutually exclusive events that can't happen at the same time. So if we're rolling a dice, you can't roll both a 1 and a 2 at the same time on one dice. So we call that mutually exclusive. Inclusive events can happen at the same time, though. So rolling a 1 or an odd number. Obviously, 1 is an odd number, so it can be both 1 and odd at the same time. It can't be both 1 and 2 at the same time, but it can be both 1 and an odd number at the same time. Oh, go ahead and pause it here and copy this down if you need, and then move on to the next one. So some examples of that. All right. So example 1. Some probabilities here. Drawing a 7 or a 9. So first of all, this is our exclusive event. If we had to say that that's exclusive. Now, the way to approach this would be to just think about, how many 9s do you have? How many 7s do you have? So how many total cards are there? So our 7s are here. There's 4 of them. Our 9s are here. There's 4 of them. So that's a total of 8 over 52. Oops. So 8 over 52, which would reduce to 2 over 13. Okay. Let's see. Let's clean this up a little bit. All right, so now drawing a jack or a heart. Now we've got an inclusive event because it can be both that is my I and an N for inclusive. It can be both a jack and a heart at the same time. So now we can think about it the same way as we did before, just how many total cards could be a jack or a heart. So I've got 4 jacks, and then I do have 13 hearts. However, I have to make sure not to count that jack twice. Is the issue here. So the total number of cards that I just highlighted were 4 jacks plus the 12 other hearts, which would be 16 total. Oops. God darn it. I'm not feeling very well. And my dexterity and my awareness of how to use this software is not very good at the moment. But anyway, it's 16 out of 52, which that would reduce to, I believe, 4 out of 13. All right. So moving on. Get rid of that stuff. So drawing an ace or a black card. Kind of a similar deal here. First off, it's inclusive, right? And we can think about it the same way. I've got 4 aces, and then I've got all these other black cards, and if I total all of them up, I believe it is 28 total cards over 52. So 28, dang it, I did it again. 28 over 52, which would reduce to 7 over 52. All right, so Venn diagrams. There's some specific problems that we're going to use Venn diagrams to solve for. This is an example of Venn diagram. It's the yellow circle are all of the circles, the blue circle are all the diagrams, and where they intersect are Venn diagrams, which are diagrams with circles. Another Venn diagram, gross food versus delicious food, where those two items intersect, are hot dogs, which are kind of both gross and delicious. Bears, black bears, polar bears, when you cross them, when you get that intersection, that's your panda bears. And we'll take a look at this one tomorrow and see if you guys can figure it out. Okay, so here's the type of problem that we're doing. Read through that. and pause for a second and then watch how it's done. All right, so my Venn diagrams, I like to start out with a big rectangle. And this rectangle represents all of the students who were surveyed in this case. So that is the population of 15,060. And we got two circles. I'm going to make a big intersection so I've got plenty of room to write. So we've got two groups, 840 seniors and 630 people who read papers. So this is going to be the one on the left. We'll say that's your seniors. This is your paper readers. There are 840 total people in the circle. Now I'm going to write that down here on the bottom because it doesn't tell me like how many people are in this section of the circle or in this section of the circle. It tells me how many people are in the entire circle. And so then 630 I'm going to write down here to tell me that there are 630 paper readers. Oops. Oh, darn it. 630 paper readers who are in this entire circle, not just in this portion or in the intersection. All right. So now the rest of the okay, so 840 were seniors, 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were not seniors. So of my three groups here, I've got seniors who didn't read a paper, seniors who do read a paper, and then non-seniors who read a paper in the rightmost section. So that 215 goes right here. All right, now I can just piece together the rest of the information, meaning what number goes here in the intersection and what number goes here. Now, the number here in the intersection and this 215 should add up to 630. And so 630 minus 215, that is what? 415. So there's 415 people who are both seniors and read a paper. Now again, the last one to fill in would be this part right here. Now that missing number plus 415 should equal that 840. So 840 minus 415, and that is 425 people. All right. Now I should have all the information I need to solve this. What is the probability that a student was a senior or read a daily paper? So what that means is we've got our seniors who read a daily paper and our seniors who didn't and seniors who did read a daily paper. Those are all of the senior. So all of these people are seniors, plus these people who read a daily paper who were not seniors, adding them all together and putting that number over the total number of students who were surveyed, which is 1,560. So for our final answer, adding all of those numbers up, and it depends, you're not always going to add all three of them. Sometimes you're only going to take one or you're going to take two. Just depends on how it's worded. All right, so the top equals 1,055 over 1,560. That fraction reduces, but if we want to just leave it like that, that would be perfectly acceptable. So I'm going to leave it like that on here. All right. Go ahead and try this one on your own and pause the video, and then we'll take a look at it, unpause it when you're done, and we can go and see how I do it. All right, so again, I'm going to start out with a big rectangle. We've got 160 beauty spa customers, so that rectangle has a total of 160 people. Big circle on the left, big circle on the right. We've got two groups. 96 had a hairstyling, so those are hair people. There's 96 of them in that circle. And then manicures. Those had 61. And there were 28 who only had a manicure. So of the groups, we've got the only hair people, the only hairstyling, the hairstyling and manicure, and the only manicure. So that 28 is going to go here, where they only had a manicure. To find the middle section, we're going to do 61 minus 28, and that is 33. Then to find the left section, we're going to do 96 minus 33, and that is 63. All right, so what is the probability that they had a hairstyling or a manicure? So this is going to be another one where we have to add all three, because the people who had just a hairstyling, had both, or just a manicure all fit into this hairstyling or manicure. What we're actually asking here, who had a hairstyling or a manicure. A lot of times students think that it means one or the other and not both, and so they don't add the middle one, but really you do have to add the middle one. And you might be thinking that for this one you could have just added 28 and 96, and that's true, but some of these questions that you're going to get are going to ask, what is the probability that somebody only had a haircut or hairstyling? So it'd just be the 63. Or what's the probability that both had it? So sometimes you don't have to do all three of these, but sometimes you do. It just kind of depends on the problem. It just so happened that both of these examples had sorry, I was adding and trying to talk at the same time. It just so happened that both of these examples we had to add all three numbers in the middle. So 124 over 160, again, a reducible fraction, but we'll leave it like that for now. All right, so that's enough to get started on the worksheet if you want to take a little break. Otherwise, feel free to go on to the video for the next part. All right, so somehow I missed a slide here, and this is the formula we're going to be using for the next components. These are what are known as the at least problems. And you'll see why in just a sec. It's all problems where you're asking, what is the probability that at least two people do the same thing, or something along that nature. It's all these at least problems. And what we're doing is using the complement to figure out the probability. We can't find the probability directly of something that will happen, but we can figure out the probability that it can't happen and subtract that from 1. Is this part of the equation tells us the probability that everybody buys something different. And if we know what the probability is that everybody buys something different, we can subtract that from 1 to figure out the probability that at least 2 people bought the same thing. Okay, so in one day, 5 different customers bought earrings from the same jewelry store. The store offers 62 different styles. Find the probability that at least 2 customers bought the same style. So what we are doing here, if we back up. Okay, so that is 1 minus NPR over n to the r. Now there are 62 different choices, and there are 5 people choosing. And then 62 choices raised to the 5th power. What this tells us, this is the number of ways that everybody could choose something different. order matters. Nobody can choose the same thing. It's 62 times 61 times 60 times 60, 59, times 58. So the probability that all 5 people, like, first person chooses one and then the second person can't choose that same thing. This is the probability where they could all choose the same thing or all choose something different. So everybody has 62 choices. Now we plug all this in and we get 62 math, PRB, NPR. 5 is a big number. 776,520,240 over 62 to the 5th. This is going to be another huge number. 916,132,832. Now, if you plug all of that in, that is going to equal, so 1 minus 776,520,240 divided by 916,132,832. You get that the probability that at least 2 customers buy the same is approximately 0.15. So about a 15% chance that if they all do it randomly, at least 2 of them will choose the same thing. All right, try this one on your own. It's really kind of, the nice part about these is they're all sort of the same problem. All right, so we've got 5 friends going dress shopping, 12 dresses in stock. The 12 is the first number, the number of dresses. The 5 friends, that is the second number. The one big mistake that students will make here is they try to include this 2 somewhere, the at least 2. I think because sometimes students just want to take the numbers that are in the word problem and insert all of them into the formula, but that's not the case here. That 2 is really, it's not meaningless, but it doesn't have any bearing on what you actually plug into the formula. It's not part of the formula. All right, so 1 minus 12p5 and 12 to the 5th. That is 12 math, PRB, NPR, 5, 95,040, and 12 to the 5th is 248, 832. And that, if we plug all of that in at once, is approximately 0.62 or 62%. All right, so there's a worksheet on Canvas. Please start that. Have some questions for tomorrow when I get back to school, and we'll start reviewing for the test.